All right, so in this section, we got a couple of, well, I think three major theorems that we're going to focus our videos on discussing and going over the proofs of, uh, going the proofs over them. We're going to go fully in depth on the proof, or maybe just a sketch of a proof, what it would look like, right, and see if you guys can take it from there on your own. But this section really just ties together the idea of non-singular matrices and inverses. Right, and what does it mean to be an inverse, and what's the essentially the excuse me. All right, how to determine if matrix one matrix is the inverse of another by performing one calculation, right? As opposed to previously sections had us multiplying the right and the left on the right and the left of a matrix, and that resulted in the identity, and then we define that to be the inverse. But we'll see here that we don't really need to go that far. We can just show that if it works on the right side, then that is enough to prove that it is an inverse matrix. All right, but before we get into that, all right, that far, we'll start off by introducing our first theorem here. Right, so our first theorem, so let me switch over here to our textbook here. And this is, again, we're in section MINM, matrix inverses and non-singular matrices. So we're seeing that we're going to establish some connections here between both of these things. So here, I'm looking at theorem NP-NT. Now this states non-singular product has non-singular terms. Okay, so it says suppose that A and B are square matrices of size n, right? So size n, whatever size that may be. The product AB is non-singular if and only if A and B are both singular. Okay, so now we have a very strong connection here, right? This if and only if is an equivalence type statement, right? Signaling inequality here. So here, let's write that down, right? So here, right? So we're working with theorem, N, P, N, T, right? And here it says AB is non-singular, right? If and only if A and B are both non-singular. Okay. So this equivalence statement, if and only if, right? It means there are two parts to this proof, right? Now, the first part we'll take to be if AB is singular. Excuse me, if AB is non-singular, then A and B are non-singular. Okay. So the way we have written this statement here is what's called an implication. So we have an if-then statement. If you take in any logic, right? We have P being our hypothesis, and then Q being our conclusion here. So what I'm going to do here, so I'm going to construct a proof, right? But I'm going to take a different approach. I'm not going to go straight what's called a direct proof, where I focus on my statement P, and then using that to prove my statement Q. Instead, what I'm going to do is I'm going to focus on something called the contrapositive. So the contrapositive is, so we negate the conclusion, and that implies that with the negation of P. And these two are equivalent So what that means, if I prove either one of those, then it's equivalent to proving the other one, right? So almost indirectly, if I have P implies Q, I'm actually gonna prove not Q implies not P. So in terms of our statement, what that means here is we negate the conclusion. So here, the statement I'm gonna prove if A, now this is an and statement, the negation of that is or. If A or B are singular, right, we're negating it, right? So the opposite or the negation, the false statement of this, so non-singular, the other thing would be singular. If A, and again, keyword there, or singular, right, then AB is singular. All right. Okay, so let's start by proving this, right? So we're going to be two cases to this proof. Now the first case, case one here, let's assume B is singular. All right. Okay. Now, again, right, when constructing a proof, right, I want to start with my statements here and look at what does it mean to be singular, right? We have a definition of a singular matrix. Right, now in general, in terms of linear systems, so what this means is that if B is singular, that means there exists a vector Z which is not the zero vector, such that B times Z is equal to the zero vector. Okay? Now again, let's stop here and just convince yourself why this must be true, right? This must be true, right? Because what did we say about, what do we know about singular matrices is that there are non-trivial, right? I'm guaranteed a non-trivial solution to the homogeneous system. So this is a valid assumption, right? Again, I don't know what the matrix B looks like. I just know it's singular. That means that it has null space, right? Another way to talk about it, right? That the null space is the non-trivial null space. So it includes something more than just a zero vector. Okay, so I can make this statement and it is valid, right? There is a Z that is the not zero vector. Okay, so I'm gonna hang on to that, right? Remember this part here, right? As I move forward here, right? So let's start off with here. Let's say, again, I'm trying to show that AB is singular, right? So let's start with, so the goal here, right, AB. So I'll start here, right? So I know Z is a non-zero vector. So if I can show that this product here leads me to the zero vector, right, that means that, again, right, think of it in terms of, so I want to show that this is true, right? All right, and what does this do, right? Z is not a zero vector, right? That means that I have a non-trivial solution to the homogeneous system. And again, I can interpret that as AB being a singular matrix, okay? So again, that's why when you're working with these proofs, focus on these definitions, these properties. That is what's going to get you to the proof, right? To get a valid proof here. Okay, so let's start here, right? So here I want to show this, so I'll start here, right? I don't know this just yet. Okay, so I'll start here, and again, I'll just use properties of matrix multiplication. Now I know matrix multiplication is not commutative, but it is associative, right? This is a valid operation here. Okay. All right, and then again, now the way we constructed Z, what is Z equal to? That's the B times Z, excuse me, that's the zero vector. So we get A times the zero vector All right, and then here, right, remember this is n by n, this is n by 1. So we get another column vector, but the 0 vector times any matrix gives me back that 0 vector. So now, what have we shown here, right? Bringing this down here. We have shown that this is a true statement, right? All of these have been valid. So here, again, this is matrix multiplication is associative. Okay, and then this was part of our hypothesis that we could set it equal to 0, right? Since B is singular, right? Those were our hypotheses, all right? And now here we have shown that this is, if this is true, we have therefore AB is singular, because I have found a non-zero vector that gives you that is a solution to the homogeneous system. So that was case 1, right? So there is one more case to consider, right? Now for case 2, right, and the reason we need a case 2, right? You think, well, I can just, it says or, right? So 1 being singular kind of satisfies the proof here. Well, since we are talking about matrices here, right? Or case 1 can lead to maybe A is singular as well. All right. So now let's take a case 2 and we're going to suppose that A is singular. Not only that, right? A is singular and B is non-singular. So that is the second case, right? The first case just focused on B being singular, right? And A may or may not have been. But here we're saying A is singular and B is a non-singular matrix. Okay. And again, what does it mean to be non-singular and versus singular, right? So let's start off with, again, if A is singular, let's come up with some vector y, where y is not the 0 vector. Okay, so such that ay is equal to the 0 vector, right? And I know that exists, right? I know it exists because that is the definition, that is one of the properties of a singular matrix, right? That non-trivial solutions to the homogeneous exist. Okay, so let's look at what type of properties we can derive from B, right? So if B is non-singular, then the linear system BY has a unique solution. Right, I think we this was one of the properties of that NME theorem, right, where all these were kind of equivalent statements, right? B being non-singular, right, then in reduced row echelons to the identity, meaning that it has a unique solution for any linear system for vector y or whatever we want to call the vector B, right? So what that means is that, again, remember, y is non-zero. So what this statement means is that there exists a vector W such that when you multiply it by the matrix B on the left, then you get this vector Y, right? And again, since Y is non-zero, B is also not the 0 vector, or excuse me, W is also not the 0 vector. Okay, all right, again, all of these are coming from either straight from the definition or basic properties that we've gone over for these types of matrices, singular versus non-singular. All right, so with that in mind, let's start off with this operation here, right? So what we have here is, right, the AB times W. Now the fact that W is not the 0 vector, if I'm trying to show AB is singular, I would like to show that this quantity is in fact equal to the zero vector, right? Meaning that there's a non-trivial solution, meaning that AB is singular, right? That's the thought process here. All right, so I know that matrix multiplication, not commutative, but is associative. All right. Okay. All right, excuse me, I was running out of power here. Okay. So not commutative, but is associative, so we can write it like this. And we said that again from our assumption. All right, so matrix multiplication is associative by our assumption here of properties of, excuse me, non-singular matrices. I can be W is Y by our assumption, but also from our assumption here, A times Y is the zero vector, right? Or Y is the solution of the homogeneous, a non-trivial solution of the homogeneous system. Well, what have we shown here, right? Since W is not the zero vector, right? That means we have a non-trivial solution for the homogeneous system. So that means that therefore AB is singular. Okay? All right. And that is it, right? Again, from the definition. That's how we prove it, right? Not from the properties or any other theorems. So, excuse me, let me restate that. This is how we prove a given statement, right? We focus on definitions or properties already derived, right? We reference those, right? Not what our understanding is of those, but those actual properties, right? I want to reference them. What does that mean? And put them into our proof, right? As statements. Okay, now that's the first direction. The other direction would be if A and B are non-singular, so now we look at the individual ones here. And then A, B is non-singular. All right. Okay. So I won't go through this proof here, but I mean, I think it'd be a good exercise, and you know what I mean, to do this on your own here, right? So what you want to do here is you want to start here. Right, and just kind of define to be x be some element in Euclidean space here. All right, and you want to interpret x here as kind of the solution to the linear system of the homogeneous system AB and the zero vector, right? It's a homogeneous system. And then go from there, right? Look at the properties that we're assuming, right? So here is what we assume. A and B are non-singular. So interpret that and determine what properties you can derive from a matrix being non-singular in terms of our linear system. Okay. All right, so here, let's move on then to our second theorem here. Now this one here is called theorem OSIS, and let me switch over to the textbook here so we can kind of go through it together. All right, now Okay, so theorem OSIS, one-sided inverse is sufficient. So what this theorem states is, suppose A and B are square matrices of size n, such that A times B is In, then B times A is In. Okay, so here let's work through this, and then we'll at the end we'll kind of debrief as what this means in terms of inverse matrices. All right. So for theorem OSIS, right? So again, it states that if AB is the identity matrix, then B times A is also the identity matrix. Okay, now, so let's start our proof here. Now, one thing to keep in mind is that In is non-singular. Okay. All right, and again, right, you can, right, all these other values are 0. And we can see here, right, we can verify however many ones we happen to have here. Right, if we perform the calculations for the identity, what we see, we'll get back the same matrix, right? It is its inverse, its own inverse as well. Okay, so In is non-singular. So from our previous theorem, NP&T, if A times B is equal to a non-singular matrix, right? So then that means that here, what that theorem tells me is that A individually and B are non-singular. All right, and in particular, we'll focus on the matrix B just because of how the multiplication is going to be set up. In particular, we have if B is non-singular, that means that there exists some matrix C that I can multiply B on the right to equal to the identity matrix. All right, that was one of our theorems here that related non-singular matrices, right, with the identity. Okay, so B is non-singular, so that means that this matrix C exists. So let's start off and let's say, all right, let's start with BA, and BA times In, I could write like this, right? Again, the way you want to think of the identity matrix is really like multiplication by 1. So it really doesn't change the product BA. So, and so that technique still holds, right? Mathematicians love to just multiply things by 1. In this case, well, 1 is the identity matrix, right? So by the inverse of a non-singular matrix, right, the way we defined it here, I can write BA, In, I can write as B, C. Right? So we have inverse of a non-singular matrix. Okay, and now again, matrix multiplication, not commutative, but it is associative, right? So I can do something like this. So matrix multiplication is associative, right? And from our assumption, A times B is In, right? The identity. right? And this is our hypothesis that allowed me to make this case. And here multiplication by the identity yields just the product IN. And then from our computing inverses, this B times C, I'm guaranteed to get the identity matrix, right? Okay, so what that means is that now we've concluded our proof, right? We assume AB gave us the identity matrix, and then we prove that if that's true, BA will also give me the identity matrix. Now, in terms of the results of our work, right, previously, right, in order to prove that a matrix B was the inverse, we would have to verify these quantities, right? All right, we would have to do AB and confirm that it was the identity matrix, and BA and confirm this is the identity matrix. Now, we can do either one, right? If I'm given two matrices, A and B, and I'm told that they're the inverse of each other, then we can do this, or we can do this. So we've cut our work by 50% here. Okay, so that's what this theorem is telling. All right.